Welcome, everyone. Imagine yourself stepping into the legendary cockpit of the Flabob Express, a classic Douglas DC-3. As we begin Chapter 1 of our pilot training series, we are focusing on a concept that is the heartbeat of flight safety: approximate stalling speeds. For a professional pilot, the stall speed isn't just a static figure in a manual. It is a living boundary that changes with every move you make. Today, I'm going to tell you the story of how this aircraft breathes and reacts as it approaches the limits of lift. We aren't just looking at charts. We are learning to anticipate the aircraft's needs before the wings stop flying. Let's dive into the systems and physics that define the edge of the envelope for this aviation icon. In the world of aerodynamics, stall speed is a moving target. It's a common misconception that it's a single fixed number. In reality, it's a dance between four key variables. First, weight. As the aircraft gets heavier, it must fly faster to generate the lift required to stay airborne. Second, the bank angle. When you turn, you increase the load factor on the wings, which sharply raises the stall speed. On the flip side, we have flaps, our best friend during landing. Extending them allows us to fly much slower while maintaining control. Finally, a bit of good news. The landing gear position has no appreciable effect on the stall itself. Understanding these shifts is what allows a pilot to fly the perfect approach speed, tailored specifically for the day's weight and atmospheric conditions. Now let's look at the North Star values for the DC-3, the certified speeds. These are calculated at maximum takeoff weight with the power off. Our VS0, the stalling speed in the landing configuration with full flaps, is 69 knots. If we raise those flaps up and fly in a clean configuration, our VS1 increases to 79 knots. This 10-knot difference is the margin that flaps provide. Remember the rule of thumb. Your final approach speed should always leave you a comfortable cushion above that 69-knot threshold. Even though the gear doesn't change the stall speed, keeping these certified numbers in your mind ensures you never accidentally find yourself on the wrong side of the lift equation during those critical moments before touchdown. Let's get into the specifics with our first data table. This chart shows us the relationship between gross weight and flap settings in level flight. Notice the trend. As the weight drops from 33,000 pounds down to 21,000, the stall speed drops significantly. For instance, at full flaps, a heavy DC-3 stalls at 65 knots, but a light one stays flying all the way down to 51 knots. A professional tip for you. Our manual's operational max weight is actually 26,900 pounds. When you're flying at that weight, you'll need to interpolate between the 25,000 and 27,000 pound rows to find your precise target. Precision here is the difference between a rough landing and a masterpiece of aviation skill. What happens when we start to turn? This is where bank angle comes into play, specifically with full flaps extended. When you bank the wings, you're essentially making the airplane heavier through centrifugal force. At a 30-degree bank, your stall speed might only climb by about 5 knots. However, look at the jump when we hit a 45-degree bank. That 51-knot stall speed for a light aircraft suddenly shoots up to 61 knots. For a heavy aircraft, it jumps to 79 knots. This is why it matters so much in the landing pattern. A steep turn near the ground can raise your stall speed by roughly 20% in an instant. The lesson here is simple. Keep your bank angles modest when you're low and slow. Now let's look at the most dangerous configuration, flaps up. This is the clean configuration, and as you can see, the speeds here are the highest across the board. In level flight at max weight, we are looking at 76 knots. But if you were to pull a 45-degree banked turn while heavy and clean, your stall speed skyrockets to 91 knots. That is a massive difference from our 69-knot landing speed. It's important to note again that even in this high-speed configuration, the landing gear being down won't help or hurt your stall characteristics. When you're flying clean, you have much less room for error, and you must respect the higher speed requirements to keep the air flowing smoothly over those massive wings. As we move to the quarter flap configuration, we start to see the transition. These settings are often used to bridge the gap between cruise and the final approach. At this setting, the stall speeds are more manageable, ranging from 56 knots up to 71 knots in level flight. Interestingly, for those of you managing your airspeed during the descent, remember the VFE limitation. You can extend your flaps to this quarter position at speeds up to 135 knots. This allows you to start slowing the aircraft down safely. Even with a 45-degree bank, the stall speeds here stay below 86 knots, giving you a bit more breathing room than the clean configuration we just looked at. Finally, we look at the half flap setting. This is the sweet spot for many pilots during the intermediate stages of an approach. Here, the stall speed for a heavy aircraft in level flight is 68 knots. If you're performing a standard 30-degree turn, that speed only nudges up to 73 knots. Be mindful of your speeds though. Once you move past quarter flaps, your maximum extension speed drops. For half flaps, you need to be at or below 99 knots. This table, combined with the others, creates a complete map of the DC-3's performance. By knowing these numbers, you can transition from the descent to the flare with total confidence, regardless of how much cargo or fuel you're carrying that day. To wrap things up, let's do a quick self-check. These are the key takeaways you should be able to recall from memory. Remember the magic numbers: 69 knots for landing and 79 knots for clean flight. Internalize the relationships. More weight or more bank equals a higher stall speed, while more flaps equals a lower stall speed. All the tables we've discussed today are based on power-off conditions and are measured in indicated airspeed. Take a moment to look at these labels and see if you can visualize the numbers. Mastery of these speeds is what separates a passenger from a pilot. Next up, we'll move to Deck 4 to discuss the airframe itself. Until then, keep your airspeed up and your wings level. Safe flying!